Hello, welcome to the PLC Hardware in the Loop simulation video, presented by the Electrical and Computer Engineering students at Michigan Tech and faculty advisor Trever Hassell, sponsored by the Robert Cinto Corporation and overseen by Jim Wenson. The need for this project began when the Robert Cinto Corporation saw an opportunity to alleviate downtime that was brought on by necessary tests of the PLC. If the PLC test could be done inside a virtual simulation, then downtime for the physical machine would not be necessary and therefore save time and money. PLC stands for Programmable Logic Controller. These controllers are used in industrial applications for all kinds of product manufacturing. These digital controllers have an array of inputs that receive signals from the industrial machine that are then run through the written code and then sent out through one of several outputs on the PLC to control either that same machine or any other machine. Unlike other controllers, PLCs don't run on conventional C++ or Python code. Instead, they run on ladder logic, which is created more similarly to logic gates than written code. To solve this problem, our team created an enclosure that can house any Allen Bradley programmable logic controller. In this enclosure, the PLC is connected to the power supply, which receives power from the wall while being protected by fuses at multiple points. In this enclosure, the PLC is then connected to the computer, which runs RS Logix and Factory I/O. RS Logix installs the ladder logic onto the PLC, where then the PLC runs the ladder logic based on signals coming to and from Factory I/O. A difference here between the industrial application and our simulation is that in an industrial application, the inputs and outputs would come from the PLC here, while in our simulation, the inputs and outputs would come from an Ethernet cable that connects here on the PLC. This Ethernet cable then connects to the computer running Factory I/O. The tests of the PLC can be done in two ways inside Factory I/O. First, a representation of the process can be recreated using the many parts Factory I/O has to offer. A second, much quicker approach would be to arrange an array of buttons and lights to represent the PLC's inputs and outputs. Analog values can also be represented in Factory I/O using the digital display. Here, we see the display being used to count the number of cycles ran. Testing the PLC using the first method may take a long time to set up, and using the second method may be difficult to monitor all at once. So combining something in between these two options may be the best option. Switching the parts associated with each input and output in Factory I/O is very easy to do and can be done by simply dragging and dropping the desired part to the desired I/O. While the simulation runs, the PLC will be connected to the EDCA, which stands for Envision Data Collection Appliance. The EDCA monitors the I/O of the PLC via Ethernet and provides a graph of how long each step of the process takes. In conclusion, our team created an enclosure that houses any Allen Bradley PLC for office desk testing. The PLC then connects to the computer where Factory I/O is ran and can be adjusted to represent almost any application, elaborate or simple. Our team would like to thank and acknowledge Jim Wenson and the Robert Cinto Corporation, Trever Hassell, Tony Pinar, Chuck Sands, Mark Sloat, Mike Goldsworthy, Michelle Kampanen, and Michigan Tech. References for videos and images used in this presentation are now shown.